All right, so this is section 5.1, which is talking about function composition. And so if you remember in the first unit, we talked about how to add functions together, right? You could do f plus g of x, or you could subtract the functions. And we also talked about how to multiply the functions and divide the functions. Well, we're going to do divide. This function composition is actually very similar in nature, where you're going to have multiple functions and you're going to do an operation with them. Except for it's not add, subtract, multiply, or divide. What function composition is a substitution. So you're putting one of your functions into the other function. And so instead of seeing an add, subtract, multiply, divide, here's the symbol that you're going to see. You're going to see this little open circle. And that will represent the word of. So when you read this, it would be g of f, and then this is of x, and that's going to be equal to plugging in f of x. So you're going to take your f of x function and plug it into your g function. So it's not an add, it's not a subtract, or a multiply or divide. It's a composition in terms of you take one function and plug it into the other function. And they're called composite functions, or you could hear them being referred to as a composition. All right, so here is a couple of questions to get us started. So these are compositions. If you notice, it's not add, subtract, multiply, or divide. It's technically this function being plugged into the other function. So what we're going to do first is we're going to find g of 0 first using our table. So where x is 0, g of 0 would be 2. What that means is that now we are looking for f of 2. The 2 is getting plugged into the f function. It's not the 0 going into both functions. The 0 goes into the g function. Whatever you get there will go into your f function. So f of 2 is equal to 8. So this composition, f of g of 0, is equal to 8. All right, same thing here. F of 2, that value will be going into g, so you have to figure out this value first. Well, f of 2 is equal to 8, so we're going to plug 8 into the g function. So we are looking for g of 8. So g of 8 is equal to 0. So g of f of 2 is equal to 0. All right, the next one we have f of 6. There's a lot of ofs in there. So the first thing you're going to do is find f of 6, and then you'll plug that value into f again. So f of 6 is 0. So in the composition, you're now looking for f of 0, and f of 0 is equal to 3. All right, and last but not least, if you want to hit pause and try it on your own, and then come back. G of 5 is 3, so then we're looking for g of 3, and g of 3 is equal to 5. And so it's a kind of a different operation here. It's not add, subtract, multiply, divide. It's this idea of this substitution, essentially. You're figuring out one of the values and then taking that value and plugging it into another function. All right, so it's this composition idea. All right, so we have some more compositions. This time, instead of a table, we have a graph here. So we're still going to find the inside piece first, and we're still going to take that value and plug it into the outside function there. So g of 2, you're going to go to the graph at g. The x value is 2. The y value here is 0. So that means that you're looking for f of 0. So going to your f graph, you're going to plug in 0, which would be this point up here, and its value is equal to 1. It's pretty obvious, I think. So 1. So f of 0 is equal to 1. So f of g of 2 is the same as f of 0, which is equal to 1. All right, f of 3, we're going to calculate that value first. So here's 3 on the f graph. F of 3, that would be 4. So we're going to plug 4 into the g function. So here's the g function at 4, and its value is 2. So g of 4 is equal to 2. All right, next one, f of 0. So first finding f of 0, we said f of 0 was 1. So now we're going to find f of 1. Well, f of 1 is this point here, which is equal to 3. And last but not least, if you want to hit pause again and try this one on your own, you can give it a shot. We're going to find g of 5. Well, g of 5 is this point here, and g of 5 is equal to 5. So this one's kind of unique because g of 5 is 5, so that means that we're plugging 5 into the g function again, and that is equal to 5 again. And so this can happen where g of 5 is 5, so we're finding g of 5, which is 5, and you kind of have a repeated point here that you're taking a look at. It can happen, it doesn't always happen. All right, so now we're going to get into talking about compositions when we have equations. All right, so here we're still calculating at specific values. So for this first one, we're going to find g of 0, and then we're going to plug that value into the f function. So first up, what is g of 0? Finding this piece right here. So that just means plug 0 into the g function. So that would be 7 minus 0 squared, which is equal to 7. So then we're going to take that 7 and plug it into f. So f of 7 is equal to 2 times 7 minus 9. 14 minus 9 is 5. So f of g of 0 is equal to 5. So you took your answer from g of 0 and plugged that into f. All right, part B is the opposite way, finding f of 0 first. So f of 0 would be equal to 2 times 0 minus 9, which is equal to negative 9. And then taking that value and plugging it into the g function. So 7 minus, and then I'm going to put this in parentheses to make sure I get the right value there, negative 9 squared. Negative 9 squared is 81, and 7 minus 81 is negative, oops. Sorry, my pencil broke, hold on. All right, back and running. So that's negative 74. So g of f of 0 would be negative 74. So this one's kind of interesting because if you do f of g of 0, you get 5, but if you do g of f of 0, you get a different number. So make sure that you're careful on the direction that you do the composition, that you do the inside piece first and then the outside piece, because if you reverse them, you will most likely get a different answer. We will see a few in the next section, I believe, where when we do this, we get the same thing, and we'll talk about that special relationship, what's happening when you do those compositions and you get the same value for both the directions that you compose. But just know that's a special case. In most cases, when you do that composition, you're going to get different values there. All right. So moving on to some more compositions, but these compositions are of x. So if you notice, all of these are of x, which means that we're not plugging in a specific value here. Instead, what we're doing is we're going to use the equations. So we're going to plug one equation into the other, vice versa. Or I guess technically when you see f of f or g of g, you would plug it into itself. All right, so this is a different notation that we saw at the very beginning. And when you're doing this other notation, it's these two right here that are directly next to each other. So g of x is going to go into f, is how that will work. So if you want to say f of g of x like this, it's the same as saying f and then parentheses g of x going into it. This one tends to be used more because it's less parentheses, and so it tends to be less confusing. I guess it's actually the same amount of parentheses, right? 4 and 4, but this one has like a bigger set around this. So just be prepared to see them in either format. All right, so what we're going to do for this problem is we're going to take g of x and we are plugging it into f. So f is our function and g is the one that goes in. So when you write this, you're going to follow the f function, and every time you see an x, you're going to take out that x and plug in the entire g of x function. All right, so f of x starts with x squared. So instead of x squared, you're going to take out the x and you're going to plug in all of g of x, which would be x plus 9. So you'll have x plus 9 squared. And then still continuing with f of x, you have plus 9x, but we're taking out the x and we're plugging in g of x. So we're going to plug in x plus 9 again. So this function should have the same powers, the same coefficients as your f function. The only difference is instead of an x, you see an x plus 9. All right, we do have to simplify this. So I do have to go ahead and take care of this x plus 9 squared and distribute combined like terms. So x plus 9 squared is x plus 9 times x plus 9. And you've probably multiplied this a ton of times, right? X squared plus 9x plus another 9x will give me plus 18x, and then plus 81. And then here on this distribute, we'd have another plus 9x and another plus 81. So combining all your like terms, x squared plus 27x plus 162. So f of g of x is going to be equal to x squared plus 27x plus 162. So unfortunately, when we don't have the values that we're plugging in and we're just plugging in the variable and we're just working with variables, we're going to have to do some more algebra here to help us simplify. All right, so here's part B. We're doing g of f of x. So f of x this time is going to go into the g function. So we're doing it the reverse of what we just did. So you're starting with your g function. That's going to be your main function. And anytime you see an x, you're plugging in your f of x function. So as I write the g function, I start with x. So in its place is going to be x squared plus 9x. And then I have a plus 9 from the g of x. So there'll be a plus 9 at the end of this. So this piece right here, that's the x portion that got replaced with the f function, that piece. And then there's the plus 9 from the rest of g of x. All right, and this one doesn't have any like terms to combine. There's nothing to distribute, no simplifying necessary, so that will be our answer. X squared plus 9x plus 9. All right, part C is f of x. So that means that you're going to take f of x and plug it into f. And so you're going to have a base of f. That'll be kind of like your base equation that you use. And then every time you see an x, you're going to plug f of x in again. So your base equation is x squared, right? So you're going to have to get rid of the x and put in something squared, plus 9 times x. And you're going to get rid of that x and put in the thing again. And the thing that goes into both of these is f of x. So in both of them, you're putting x squared plus 9x. X squared plus 9x. So the setup on that one I think is a little bit different, kind of unique that you take a function and put it into itself. And then unfortunately, we do have some algebra we can do here, right? So this squared here at the beginning means you have to take x squared minus or plus 9x and times it by itself. So you're going to have to distribute. X times x squared would be x to the 4th. X squared times a 9x, that's a plus 9x cubed. And then distributing this one, same thing. 9x times x squared would be another plus 9x cubed. And then 9x times 9x is a plus 81x squared. And then you do distribute this 9 into here as well. So we'll have a plus 9x squared and then a plus, I'm running out of space, but a plus 81. Oops, sorry. Plus 81 there at the end. And then just combine your like terms. So x to the 4th is by itself. We have 9x cubed and a 9x cubed, so it'll be an 18x cubed. We have an 81x squared and a 9x squared, so it'll be a 90x squared. And then that 81 is the only constant there. So plus 81. I did mess this up, didn't I? I was like, wait, something's weird going on here. When I rewrote this one, I didn't write f of x exactly, did I? So I had x squared plus 9x, and then I put x squared plus 9, and there should be an x here, which is not too bad of a mess up. It just messes up this 81 at the end. It should have an x with it, so that should be 81x. Sorry about that. All right, so then the answer for this composition would be x to the 4th plus 18x cubed plus 90x squared plus 81x. So A and C were a lot of work. Part B, that was like hardly no work at all. So hopefully D is a little bit easier. So let's try part D. So we have g of x. So you're going to start with the g of x, and where you see that x, you're going to plug in g of x again. So you're going to have x plus 9. That's the substitute in for the x. And then you have a plus 9 from the original g of x. So once again, this is the x piece from the original. So x plus 9, but you got rid of this x and put in x plus 9. So that's what's happening there. So this one was pretty easy, x plus 18 for the algebra. As long as you got the setups can get a little confusing. So as long as you get the setups, then it's just algebra from there. All right. Moving on, we're going to do some more compositions, but we have some different kind of equations. So that last one that we did, we had a quadratic and a linear. Here we have a square root and a line. But even with the square root, it's still a composition just like we've been doing. You still are just going to plug one function into the other based off of the order that it's written. So in this case, we're doing f of g of x. So g of x is the function that is going to go into f. So we're going to start with our f equation. So 3 minus the square root. And instead of that x, we're going to put in the g of x. But it'll still be squared and still have the plus 1. And so in here, where that x was, you'll put in x minus 5. All right, you can do this distribute in here and combine like terms. So this would be x minus 5 times x minus 5, right? So that would be x squared minus 5x, so minus 10x, and then plus 25. But then you have the plus 1 at the end. So is everybody okay if I just erase that and say plus 26? So it's 25 from the distribute and the plus 1 here, making that a 26. So underneath your square root, you have that quadratic. And then the 3 minus in the front. And there's not really anything else you can do to simplify this. So it's 3 minus the square root, x squared minus 10x plus 26. Make sure when you're putting this into MyOpenMath that the square root goes all the way across. If you end your square root here, it's going to mark it wrong. Or if you end it here, it's going to mark it wrong. So make sure it goes all the way across there. If you want to kind of guarantee, you could put that in parentheses. That might help. But most likely, if you get something wrong, it's because of the way that you're inputting it in there in terms of that square root. All right, the second one says find f of g of 0. And so you have two options here. We already have the equation for f of g of x. And so all we have to do is plug 0 in here for both of these x's. That's option number 1. Option number 2, if you wanted to, you could first find g of 0. So you could put in 0 here. and then get your value and then plug that value into f. And so 2 options, and it really doesn't matter how you do it. So I'm just going to go ahead and use the fact that I already have the equation for f of g of x to find f of g of 0 by just plugging in 0. So if you plug in 0 here, 0 squared, 0 minus 0. So all of those will go away and be 0. So the inside of that square root is just 26. And you have 3 minus in the front. So we have 3 minus the square root of 26. And if that square root simplifies, you should simplify it. Say 25 would be a perfect square root, but I don't think it has any other perfect squares in it. There's no 4 in there. There's no 9 in there. No 16. The next one's 25. So yeah, so this is as fully simplified as it's going to get. But it does say, I just read this, it says round your answer for the second part to 2 decimal places. So it really doesn't want this. It actually wants the decimal equivalent. So let's go ahead. We'll type it in our calculator. We have 3 minus square root of 26. Didn't hit the right square root. Hold on. Square root of 26. So we have negative 2.099, and it says to 2 decimal points. So it would be negative 2 point, and we would round here, so the 9 would round that up. So negative 2.10. All right, so always make sure you pay attention, right? It says round it to 2 decimal places, so it does want a decimal answer in for that one. All right, up next, another composition, but this time we have fractions. So this is a rational function. This is also called a rational function. We are going to talk about rational functions in more detail later on this trimester. There's a unit that has to do with rational functions. But right now, we're just going to work on the algebra associated with a composition here. So the first thing we're going to do is we're going to find f of g of x. So we're going to take g of x and plug it into the f function. So you're starting with your f function. That's your base. And wherever your x was, so it would have been right here, we're going to replace that with the entire g function. So that would be 5 over x plus 3. So this piece right here was the x that got replaced. All right, and we're going to do some simplifying. In the denominator, I see 3 minus 3, so that would go away because that would just make 0. So I see 1 over 5 over x. And this is what we call a complex fraction. It's a fraction in a fraction. And so the main thing here to remember is that this fraction right here is division, right? And so what we're doing is we're dividing by a fraction. And whenever you divide by a fraction, you can take care of that by flipping the fraction over and multiplying instead. So instead of 1 divided by 5 over x, what we can say is 1 times, and we flip this fraction over to say x over 5. So dividing by a fraction means you can multiply by what is called its reciprocal. Reciprocal just means to flip the top and the bottom. And 1 times x over 5 is just x over 5. So that composition would be the fraction x divided by 5. All right, composing this other direction, we now have f going into the g function. So the g function starts with 5 over x plus 3. And we're going to get rid of the x down here from the g function and replace this piece with what we have 1 over x minus 3. All right, and let's see if we can simplify anything here. So right now, these aren't going to simplify the plus 3 and the minus 3 because they're not right next to each other. This is in the bottom of a fraction, which is actually in the bottom of a fraction, and that's just a constant. So what we're going to do is we're going to take care of this piece here by doing what we did here, flipping and multiplying. So that would be 5 times x minus 3. I'm putting it in parentheses, make sure I have both, over 1. So we flipped this fraction over, and multiplied it by the top, so 5 times that. And then there's a plus 3 at the end of this. So 5 times x minus 3 means you have to distribute and say 5x minus 15. And then this would be over 1. And by the way, dividing by 1 is kind of pointless, right? Because whenever you divide by 1, you're just going to still have what you started with in the numerator. So the divide by 1 essentially goes away. It's not doing anything. And then there's a plus 3 here. And so this one would simplify to 5x minus 12. So kind of two gross functions at the beginning. They just weren't very nice and not so easy to work with, but their compositions weren't actually that bad. It was just this is technically a line and this is also a line. And so their compositions turned into some pretty nice things after we simplified. So if you're struggling to simplify a fraction in a fraction, it's the bottom fraction flipped and multiplied. All right, we have just a handful more. So up next, it says the function h of x equals 1 over x squared can be expressed in the form f of g of x, where g of x is equal to 1 over 2 and f of x is defined as. And so what they're saying is they're saying f of g of x got composed. There is a composition that happened here. So g of x got put into f of x. And when it got put into f of x, its answer is 1 over x squared after the composition. And so what they're saying is they're saying, okay, g of x is x plus 2. What would f of x have to have been in order for this to be the composition? So this is the piece that got plugged in, right? This is the x plus 2. So what you can do is anytime you see that right there, the x plus 2, that means that in the other function there was an x there. Because the x would have gotten taken out for the x plus 2 to go in its place. So what happened here was this was 1 over x, and then it got composed with g of x, and the x left the denominator, and it became x plus 2 in the denominator because we plugged x plus 2 in. So that means the f function was 1 over x. So kind of tricky because you're kind of working backwards there to try to figure out what's going on. But when you have the pieces, try to kind of match what's happening here. So if we have 1 over x squared, or x plus 2, sorry, and one of the functions was the x plus 2, that means that that denominator had to have just been an x for that x to have gone away and x plus 2 to have taken its place. And so that's how we get the other function pretty easily. All right, up next is another composition, and this is actually quite a few compositions. Look at this. We have f of g of h of x. And so you're just going to start on the inside. You're going to start with h of x, and you're going to compose that into g, and then you're going to take that and put it into f. And so you're just working these compositions. So this is kind of like a double composition. You're not just composing once, you're composing twice. All right, so the first piece is this g of h of x part in the middle, where you're taking the h of x and plugging it into your g function. So your g function is going to be your base, so it would be x minus 2, but we're getting rid of the x and putting in h, and h is the square root of x. So when you take h of x and plug it into g, you end up with the square root of x minus 2. Now what we're going to do is we're going to take that whole thing, so we're taking this thing right here, and we're going to plug it into f. So now we're putting that into f to get our final composition. So wherever you see f, or f is going to be like your base function, right? Something to the fourth plus 9. And in there, you're going to plug in where the x used to be, square root of x minus 2. All right, and then technically you could do this multiplication to the fourth power. You would have four of them. The square root of x minus 2 times the square root of x minus 2 times the square root of x minus 2 times the square root of x minus 2. You'd have four of them that you'd have to multiply together. I believe this problem doesn't require for you to do it. Typically, if it's like an x squared, then they say go ahead. But if it's something like x to the fourth, they're not going to make you do all of that multiplication out. So that composition is just equal to the square root of x minus 2, that whole thing raised to the fourth power, plus 9. There's no other combining like terms or anything that we can do here unless we do this distribute. So it's good just the way it is. All right, last question for this section is a story problem. And so it says your local grocery store is having a 15% off everything sale. But wait, for the next 3 days, they are offering a coupon to save an additional $13 on any order over $100. If the store applies the sale price, then applies the coupon, find each of the following. Also, we are assuming the order is over $100, and X is the price of any item. So X is going to be like the price essentially of what we're buying. Round all decimals to 4 decimal places. All right, write a function called the sale of x, and that's what they have here, the sale of x, that will directly calculate the final price of the item. All right, so the order that they're doing this in is the sale price, then the coupon. All right, so your sale price goes first, then your coupon, which means that when you take the price of your item, you're going to have the sale price first, and the sale price is 15% off. So how would we calculate 15% off? We would multiply it, right? Now, when you multiply this, if you multiply by 0.15 for this decimal, you're not taking 15% off. What you're doing is you're figuring out what 15% is left over. And so if you want to take 15% off, technically you want 85% of the original value. So right here should be 0.85. So what it's doing is it's taking out of the whole 100%, the actual value of the item, it's taking off 15%. So essentially what we did was 1 minus 0.15 to get how much we were actually, how much we actually were keeping. So this is how much off, and this is how much is being kept in terms of our percents. So we're going to keep 85%. So once you take your price and you times it by your 85% to figure out how much it's still going to cost you, that will take off the 15% and have how much is left over. They're also going to take off $13. So they would just subtract $13 from that price. All right, so a little weird working with those percents. So hopefully that made a little bit of sense to you. If it didn't, the next time you're in class, please let me know. Or if you need to send me an email or something, hopefully we can clarify that a little bit for you more if it didn't make any sense. All right, part B says write a function called its ELOS, which is sale backwards. They're being super creative there. That will directly calculate the final price of an item if the discounts were applied in reverse order. So now we're going to reverse it. So instead of it getting multiplied first, it has to be subtracted by 13 first. So what that means is that in parentheses, I need to have x minus 13 so that by the order of operations, that will happen first. Once that happens, then we'll take that value and figure out 15% off in terms of the 85% that's left over. So it'll get multiplied by 85 or 0.85 after you do the subtraction. So the difference here is this one does the multiplication first, then subtracts. This one subtracts, then does the multiplication. So that's how we make sure they happen in reverse order. All right, and then the final question says, which sale is better for the customer? So would the customer rather take the 15% off and then subtract 13, or would they rather subtract 13 and then take the 50% off? And so what we can do is we can pick a value of an item and we'll calculate both of them to see which one was better. Which one did they save more? So just pick the price of an item. It's completely up to you. You can go with, I just picked $150. Let's go with $150. as long as it's over 100, right? So I'm just going to assume that she's going to buy an item, or I'm buying an item, the customer, whomever is buying an item, for 150. You could say 200, you could say 250, you could say 300, you could say 485 if you wanted, as long as your number is a price over $100. All right, so here's the first one, the sale piece. And so if I put 150 into this function, I'm going to have 0.85 times 150 minus 13. And so calculating that value, we have $114.50 is how much that item would cost me. So now we're going to calculate the same value for the reverse, the sale backwards. And we're going to plug in 150 again. And we're going to see which one is a better deal. So in this case, we're going to subtract the 13 first, then times by 0.85. And I get 116.45. So if my item costs $150, with this one, I'm going to only pay $114.50. With this one, I'm going to pay $116.45. So that would mean that this would be a better deal for me because I would pay less. So in this case, it's better to do the percent discount first and then to go ahead and subtract off the value amount. All right, so that is it for this section on function compositions. So let me know if you had any questions on the notes as you were going through those. It looks like the homework, there's 29 points or 29 questions points associated with the homework. So I would go ahead and get started on those and let me know if you have any questions, what I can do to help.